So it's test 11. We've got 6 sections here, all of chapter 21, one part of 23, and then 2 parts of 25. Okay, what I want to do is talk about the ideas that you need to know for the test, the concepts. Okay, it's a very highly conceptual test. It's 80 points. Okay, give you a heads up. You're going to have about high 30s in multiple choice, high 20s in short answer, and then about 20 points worth of mathematical. So it's like almost like 40, high 30s, high 20s, and then 20. Okay?
How many is each multiple choice?
3 points. That's just a good amount of them. Okay? All right. Yeah.
There's just, so we're talking about right hand movement at one point. They were talking about like they're around a wire when you're
Yep.
your hand. Can you go over that?
Yep. That's something we're going to go over, like I said. I just said that. Now, the first thing I want to take a look at is start with magnets so we can go one step at a time. First, you need to remember, what happens with magnets and their poles? The poles have to be what to attract?
To be opposites.
Opposites to attract, like poles, repel. Right, repel. We talked about, can you hold on to it for a sec? We talked about magnetic domains. Who can tell me what was a magnetic domain and how did that affect us? Where did magnetic domain theory come into play?
Like if it's like a parts that have like different poles, then it's like all like mutually all like switching around. It's like one. What's it called? Like one like same domain.
Is it a dipole?
No, like inside objects are like different like magnetic domains. If it's neutral, so they're all aligned.
I mean they're aligned.
Yeah.
Let him talk. I know you're trying to help, but let him talk. The magnetic domains are going to be oriented at random and different angles if it is unmagnetized. And that was the example we showed with a diagram. If all the domains are aligned, that is a magnetized piece of material, whatever it may be. And that's what happens when you bring a magnet near something that is ferromagnetic. Remember, ferromagnetic has the ability to become a magnet, under an influence of a magnetic field. And the alignment of the poles will all orient themselves the same way when it's brought near a magnet. That's what's happening when something becomes magnetic.
Just really quick, my tutor used to work on a tugboat. He was saying like since it was all made out of steel and iron, like the first like when you get a brand new tugboat, in the first couple thousand miles that you do, the compass is like completely haywire because of all the iron in the boat and stuff. And then once it like goes for like 2,000 miles, that it actually the boat like becomes a compass.
And it probably has an induced magnetic field around it. That's why over time it changes. Yeah, very good application, Will. Stash, you had a question. Got it? Okay. Soft versus hard magnetic materials. There was a difference between the two. Soft versus hard magnetic. What do we got here? Hold on. Cammy.
The magnetic soft material is like, it takes a while to form. Well, it takes a while to form, but it lasts a short amount of time.
That's the hard one. The soft one is,
It takes a short amount of time.
but it doesn't hold the charge. Okay? So remember, it's like cramming versus studying. You cram, you remember short term, but then you're going to forget it.
That's hard.
That's the soft magnetically. Hard magnetically means it is hard to get it to be charged, but it maintains that charge even when you remove the magnetic field. Okay?
It's hard to get the charge, but it maintains the
But-
charge for a long time.
Even if you remove the magnetic field that's inducing it, it'll still maintain that charge. Whereas soft magnetically, the minute you remove the field, it becomes unmagnetized. Okay?
That's an example of
Yeah, can you go again like you did last time? And tell
I don't
us-
know material-wise, Fernando. I don't know material-wise. I know that iron is soft magnetic. Iron is ferromagnetic, but it is soft magnetic. I know that for an example. So iron you can make into a magnet easily, but it will not maintain that charge.
Oh yeah, that's what I was going to ask. Is ferromagnetic? What does that have to do with this? Is that an example?
Ferromagnetic means-
It's like iron. It's like an iron type material that.
But what can it do?
It's that. It's like it's used. It's also called a diploid because of when you do like the magnetic
Diploid.
field thing. When you put a magnet near it, it automatically charges and it sets to north and south.
So it can be easily influenced in a magnetic field.
So it's soft.
Not soft. It is in general. It is possible to become a magnet.
Okay. And then what do you mean by hard and easy? Like, it's just hard to be
I
magnetized?
just said that, Jeff.
It takes a long time to get magnetized, but then once you...
No, I know that, but what do you even mean by hard, like, to...
Hard magnetic means it takes a lot to get it to become a magnet. It has to be induced in a field for a long time. And it maintains that charge, though, afterward. Whereas soft, it takes nothing to make it a magnet. But it's not going to maintain that magnetic charge. Okay.
So that's good.
So, according to, we have two right-hand rules we need to discuss. The first right-hand rule was a current in a wire. If the current is flowing, say, this direction, you put your thumb in that direction. Then your fingers represent the curl of the magnetic field. Again, thumb in the direction of the current, fingers curl to show the direction of the magnetic field. Second right-hand rule was this. Fingers point in the magnetic field direction. Thumb represents the velocity or the motion of a proton. The palm represents the direction of the force. So if you had, remember this, or you do an example, a field acting upward, and you have a velocity of a proton acting west, I'm doing it in your direction, west, the field acts into the page. Into the page. Okay?
You just say
Or you could say the force, thank you, Jack, thank you. The force acts into the page, or you could say north. If this is west, and this is up, you can consider this to be north if you'd like.
Wait, what's
Or
west?
into the page.
Can north
West,
left.
up. You could consider this the force, which is either into the page or north. Either answer is fine.
On the test, can you specify, because I know you always say like downward, north, and all those are actually technical.
Your answer can be given whichever way you like. But I'll tell you north, south, east, west, up or down, or into the page or out of the page.
So north is always in front.
Like, north is this, not, and upward is this. and
That's why it's confusing. If you consider this to be north and this to be west, then you have to look in and out of the page. It depends on which way you call it. It's up to you. Either way is fine. Fernando.
We're ignoring that you two and out of the page thing. North is forward, like in front of you. South is behind you.
Sure. Yep. I would use into and out of the page because that's why I learned it. But your book says a tendency to use both, so either way is fine. Garrett.
There was a question in the problem set about there's like the magnet. How come like a magnet is attracted to the north pole, even though
Yeah, so
is it because the geographic north pole is actually the south pole?
magnetic
Magnet.
south pole.
I
Okay.
mean, I read that, but I don't think
That's correct. So
understand it.
the way it works is this. A long time ago,
Very complicated to explain.
we decided to call the North Pole the North Pole because the north tip of the needle on a compass would point that way.
Yeah.
So we called it the North Pole because north faced that way. So it was like, oh, this is pointing north on the compass, let's call it the North Pole.
But it points.
But really, it is the
geographic.
South Pole. Magnetic,
Okay.
geographically, as Jack is saying, it is the North Pole. Okay?
It's like that's what like geographically. That's what Olivia explained. Magnetic north is like south. That's
Yes.
what they use in like.
Yes.
Go true north.
Absolutely.
Magnetic actually just hangs south.
Absolutely. Solenoid. Remember that device with the wrapped wire and the current running through it?
I know it.
What three things? Most of you forgot one of them, it seems, I think, on your problem set. What three things?
I got it.
It asked for two things, but I'm asking you, there's a third, if you had to know a third. Give me, Paul.
Alright, as current increases, the solenoid strength increases.
That's one.
As coils increase, the solenoid strength increases.
Be careful. Coils per unit length, meaning the concentration of coils. Okay?
Wait, as
Coils per unit length.
And the magnetic field inside said solenoid is uniform, but outside the solenoid, the magnetic field is weak.
Okay, that's true, but that's not part of the question, Stash.
If you put a ferromagnetic opposite inside.
Yeah, that was the third. It creates what kind of a material and what? Electromagnet. That was the last part we talked about.
Can you write those down?
So if you can write it down, sure. If you put a ferromagnetic rod inside of a solenoid, it increases the strength of it because that induces a magnetic field on that ferromagnetic rod, which makes it then produce its own magnetic field. So it's amplifying it, okay? It's making it stronger.
Put a ferromagnetic rod in the tube,
Yep.
turn it into electromagnet.
Correct.
it
Paul,
turns
stop.
the solenoid into an electromagnet?
Correct.
You can say density of coils, right? The number
Yes,
of
that's fine. Density of coils is fine. But it's not the number of coils, it's the number of coils per unit length. Per unit length.
And
Mash.
What does into the page mean?
Into the page. So, if I had, ready, wash my hand. If I had a field acting up, and I had the velocity of the particle acting left, then my palm faces into the page, if this were the page in front of me. Out of the page would be this way. So if my palm faced that way, it'd be out of the page.
So it's an actual
An actual, if you had a page or a whiteboard in front of you, what would happen? Okay? Let's see. Why was Rutherford's model considered to be unstable? Why was Rutherford's model considered to be unstable? Joey?
Was it because that the nucleus was being positive and that it was centered around a bunch of electrons and people were confused if the electrons would collide with the nucleus?
Yes, very good. The idea was that these orbits would continue to, careen into the actual nucleus.
the electron.
Okay? The orbits, yeah, but the electrons in orbit, sure. So these electrons would get pulled closer and closer inward, so there must be something keeping them apart. Okay? So it was considered to be unstable at first.
Well, he also made you need to add to the radiation without, he said there's centrifugal acceleration of electrons, and as electrons accelerate, it emits radiation.
Yeah.
So that means that the atom will be slowly dying, but also emitting a lot of radiation.
And that gravitates towards the nucleus.
Okay? So everybody hear what Fernando said. Again, if there's centripetal acceleration, it's got to be giving off radiation. If it's giving off radiation, it's going to slowly be losing its radiation, or it's going to lose it's like a half-life. It becomes radioactive or unstable. But we know that most elements are not unstable.
This also has to do with the fact that
Rutherford?
had like a space, like empty space between all the electrons.
Well, the empty space was a result of his test. The test showed that only some of those alpha particles that hit the gold foil bounced off, because that positively charged nucleus was very small. That proved that there was a lot of empty space. Okay? That empty space, though, in turn, it gives us the fact that there's going to be some space between the electrons and the positively charged nucleus. Sasha,
Wouldn't it have to be negative acceleration?
what do you mean?
Acceleration. Because if it's giving off energy and if it collapses, I think if it were accelerating, then wouldn't it not collapse but leave, and then it would be absorbing.
Well, there's a lot. Think about what acceleration is defined as. It's defined as v squared over r, right? So it depends. Is the velocity increasing? Is the radius decreasing at a higher rate than the velocity is increasing? I understand what you're saying theoretically. If it's giving off energy, it should be reducing its speed, so decelerating.
Seems that the atom will collapse, but then wouldn't it have to slow down, not increase speed?
If it's giving off energy, it's losing velocity, it's losing kinetic energy, so the velocity will go down. But the radius is also going down if it were to be collapsing. See what I'm saying? So it's a question of what's going down faster, the quantity v squared or the quantity r. Okay? It's a matter of which is greater than the other reduction.
You're gonna hate me, but back in the solenoid, number of coils per unit length. What about the number of coils per unit length?
Density.
As it increases, the power increases. More coils, stronger solenoid. Jeff.
In the Rutherford model, what is preventing it from exploding? What's that? Is that we find that in the Bohr's model?
In Bohr's model, we came up with the idea that there must be some sort of a strong force in the nucleus. Strong force in the nucleus, which is also called the nuclear force between the We'll get to that if we keep going. We will get to that topic.
Wait,
Okay.
the Rutherford model was incorrect, right? It didn't work. Yeah. That's why.
Even the Bohr's model is not really correct. They're all theories, yeah.
So if that was true, then we'd all be really dead.
So it's a strong force or a nuclear force rectangles.
Yeah.
So inside the nucleus, what do we have? What particles do we have inside of the nucleus? Yeah, protons and neutrons only. The electrons are outside. Now, the force that exists between the protons and the neutrons that hold it together is called the strong force, or that nuclear force. And you need to remember that the more neutrons, the more strong force you have. But the more protons you have, the more electric force that's trying to split it apart. Okay? So you want to make a more stable element, you want more neutrons. If an element becomes more unstable, it usually has more protons. Thomas?
The number of neutrons is equal to the mass, right?
The number of neutrons is equal to not the mass. It is the mass minus the number of protons. Because the protons plus the neutrons become the mass. That was, if you remember that equation that you had. Okay? Forget what the equation said as far as, but it's mass equals protons plus neutrons. I forget what it actually said. But that's what the mass is. The protons plus the neutrons. Molly.
What does the strong force have to do with, like how heavy an atom is? Does that have anything to do with it?
The more neutrons,
If there's more neutrons, is it heavier?
it's heavier, and it also has a higher strong force.
Higher density, right? That was my question.
Higher what?
Density?
No, the density is constant. Remember we talked about that.
But the volume, though, is maybe...
But the volume's going up and so is the mass, so the density is constant.
So, but you're saying it's more compact, though. That's why it's stable?
No. The density is constant. You're asking the same question three different ways. The density is constant. Okay? It's not more compact. There are more neutrons. The more neutrons you have, the larger the strong force holding it together. If you increase the protons, though, you get this electric force that increases, that repulsive force. That's the issue there. Okay? Thomas?
And it's considered heavy if it's over 58?
58 we considered heavier, yeah, above that. Stash.
I know at the weak force, what is the strong force again?
The strong force is the thing that holds together the nucleus. It binds the neutrons.
You said it was the opposite. So the weak
The force is actually stronger.
Guys, the thing that's inside of the nucleus, that's holding together the neutrons and the protons, is considered the strong force, also known as the nuclear force. That's the only thing we really studied. We mentioned the weak force. We mentioned it, but we didn't reference it.
No, you said the weak force is the stronger one, the strong force, the weaker one.
But that's not talking about what's happening here, guys. The question you asked was this. What is the force inside the nucleus? It is the strong force, aka the nuclear force. Okay? That's the one we discussed in class. We did mention the weak force. We did. It's a whole other force that we didn't even study, though. If you want to learn more about that, that's in section 25.4. I think it's 25.4 in your textbook. Okay, it talks about the four fundamental forces. Let's see. Magnets. If you cut a magnet in half, what happens? Now, Tyson, follow up to your question or your answer. Here's the magnets. How can you identify or label them now?
On the outside of the cell. Like on the far left and far here.
Far left of here. So tell me, Tyson, once you go here. Once you go here, I can't hear you. Sorry.
North.
Good.
And then south on the other.
Okay.
And then the same thing.
Good. So that's the key here. When you break a magnet in half, the magnetic domain theory tells us that these domains are all lined up. So these are also going to be lined up even though you split it. So all these domains are still lined up. So this is going to be north now still and south. And north and south. So you create like a mini magnet of each. But it's a replica, okay, of what you had to start with.
If you had three, would you have literally just three of those?
Yeah. You can break it into a million pieces. Same difference. All right. Remember that field lines are always drawn from south to north. Magnetic field lines. Who remembers why that is? Why are they drawn from south to north?
It's because south attracts north, and the north one like accepts the attraction, and south gives off.
Hold on. Backwards. I'm saying it wrong. Hold on.
Shouldn't north be
Yeah.
south?
Going from north to south.
No, I think it's south.
It's north to south. It's north to south.
So then south is like...
I made a mistake there. Hold on, guys.
And I changed my answer the other way.
Let me explain why. Because after I thought of the reasoning, I realized I made the mistake with saying that. The direction of the magnetic field comes from where the compass would be directed, the north tip of the compass. And which way would the north tip of a compass go? Toward the south pole. Okay? So again, the reasoning, after I thought of the reasoning, that's when I was able to realize I said the wrong statement. The reasoning is this. the direction of the north tip of a compass indicates the magnetic field direction. So a north tip of a compass has got to face the south pole of a magnet.
Face north.
That's on the Earth with the geographic north. But on a compass, if it's a north tip, it's got to face the opposite. Remember, opposites attract. Okay?
Yeah, but on the compass that you're looking at, it's always pointing north.
No, true north is polar south.
Thank you.
And that's just cheap.
Oh, yeah. Absolutely, yeah. I realized we're talking about the other.
Yes.
Can I get a drink of water?
Yep.
All this intense talk.
So that's what the compass would look like, people. Remember, the colored in part of the compass is always the north part. The north part is going to be attracted to the south pole, and the angle or the orientation of the north part of the compass is indicating the direction of the field, which is why the arrow is pointing toward the south pole. Okay, toward the south pole. But you see that even though sometimes you may think one answer is right, when you go through your reasoning, you can see that actually it looks like this. And that's what happened to me there a second ago. I made the incorrect statement to start, and then I thought about, wait, what's my reasoning? The reasoning is the north tip of the compass, that faces the south pole. Okay?
Can we review spontaneous emission, please?
Like specific things.
The what?
Are you doing something?
I'm pretty sure it wasn't.
What have I been doing the whole time?
I know, I'm writing it all down. I just sometimes we do this. I'm like, oh yeah, I heard that. I believe teachers should give you the test. You study what's on the test, you do well. You're rewarded for a good grade, and you actually know what's going on. It's not considered cheating.
Your homework problems, your problem set, your notes, those are all that's on the test.
I've told every teacher this.
Terminology.
Well, I just had a question on spontaneous emission.
Okay. Question on spontaneous emission. Good topic. Okay.
Exactly like what I just not what I'm saying.
Alright, so here's spontaneous emission. A photon hits an atom. The electron absorbs the photon. The photon is energy. The electron absorbs the photon, jumps up to an energy level, to an excited energy level. It then has a desire to return to its ground state, and when doing so, it gives off energy in the form of light. This is where your spectral lines come from on that diagram.
Excited back to whatever.
Back to ground state. Ground state.
And that's when they emit and give off.
Correct.
Is this like.
What does the term isotope mean?
Oh.
Isotope. Molly.
It's when an atom can have different numbers of neutrons.
That's exactly it. Very good. That's all it is. An atom that can have different numbers of neutrons. So two isotopes would be like carbon 12 and carbon 14. Because the only difference there, they both have the same number of protons. That's the other key. Proton number never changes.
Where's electrons?
So carbon always has 6 electrons. Can change. Becomes an ion. Protons of carbon always is, the number of protons in carbon is always 6. But the number of neutrons can vary, giving it its isotopes. Fission. Neutrons vary, protons constant.
Okay, wait, and then can you give us examples?
Can the electrons and
Just
the
gave an
neutrons change
example.
at the same time?
I just gave an example.
Can electrons and neutrons change at the same time?
Like carbon.
Iso-ion?
I don't know. I guess, yeah. You could have an isotope of carbon that can then be charged. Sure. Alright. What is the difference, and in doing so, explain the processes of fusion and fission? Fusion and fission. Jeff.
Fusion is the splitting of atoms.
It's a fission.
Fission is division.
Fission sounds like it's the combination.
We're going to run out of time. You guys are not going to get the rest of the questions. And I'm not going to help you afterward if you don't.
There's no office hours?
Fusion. Fusion is two things combining into one. Fission is two things separating into one. Okay? Which of the two do we use currently in reactors? Fission. Fission.
Because fusion,
We have
like
fission
Dragon
reactors.
Ball Z is too hard to
Control.
I remember what Stas said about fission, but I don't remember what he said.
Like yesterday?
I remember
remember the division 50, but I don't remember what he said.
I just know where
I don't know, like Vegeta.
Mathematical. Mathematical. That was your first formula we had. Now, to quickly go over these in units. F was the magnetic force, measured in newtons. Q was the charge, measured in coulombs. V was the velocity, measured in meters per second. B was the magnetic field intensity, measured in Tesla.
Is it Telsa?
Tesla. T-E-S-L-A.
The car. My car, yeah.
Now,
Like the car.
in a problem like this, you also need to be able to give the direction. So that's where your right-hand rule comes into play. So if you are solving for the force, you would move QV up and you get force equals BQV. You can get a number and say 50 newtons of force, but this is where you need to give a direction. So if the problem says determine the magnitude and direction of the force, the magnitude is the number, the direction is east, west, north, south, into the page, out of the page, up or down. Okay? And that's using the right-hand rule.
Like if
You just point your finger to wherever it
like
says.
that, and then that.
Yep, it's one of those.
First of all, all you have to know is magnetic field.
Next, we did an example. We did an example where we talked about the fact that an electron has a tendency to move in circular motion when it's in an electric field. Now, if you remember, what we did was we talked about centripetal force like this, and we talked about the magnetic force like this. Okay, solving for the magnetic force in that earlier equation, we have BQV. Okay, we have BQV, and we have the centripetal force. What did we do to these two? What did we do to these two? Set them equal. We set them equal. Okay? We set them equal because the magnetic force is what keeps the object in circular motion. Now, if you're asked to find the magnetic force in one part of the problem, you can do that by multiplying BQV. And then you would have the magnetic force. Say it's 50 newtons. You would take 50 newtons and plug it in up here for the centripetal force. So say you had 50 newtons now, and you knew the mass, and you knew the radius, what could you find? The velocity, or say you knew the velocity from here. Sorry. So you would never not know that. You could find the radius, or you could find the mass. So you might be given like a two-part question here. We have to find the magnetic force first, and then use it to find the radius, or the mass, or whatever it may be. Okay? Third part for math.
I missed this entire section.
Now, this tells us the energy that is released when an electron jumps from a higher level to a lower level. That's E. Okay? So we talked about an example in class where we had 5 levels. Say level 5 was 10 electron volts. Level 4 was 7. Level 3 was 5. Level 2 was 1. And level 1 was a half of an electron volt. And let's say that the electron jumps from level 4 to level 2. What's E? From level 4 to level 2. What is it? 6. Level 4, level 2. What's the difference here, right? The difference is 6. Be careful, Paul. 7 to 1 is 6. So E would be 6 here.
Wait, Sean, is that all you do for these math equations?
Yes, for the
This would be 6. Now, H is what? Planck's constant. It's given on your test. It's on your formula sheet. Look at the updated formula sheet if you don't know where it will be. Study that tonight. It's the same formula sheet you'll get tomorrow. What does omega represent?
The jumping.
The
Power takes a jump.
frequency, wavelength.
Stash, what does omega represent?
Frequency of the light.
Frequency. The frequency of the wave emitted. It may not be light, okay? I was ignoring them there, that's why.
What is omega? Just do you stuff.
Omega is the frequency measured in hertz, Hz, and it represents the frequency of the wave. Now, remember, if I give you a table and it has a whole bunch of frequencies, you might have to say it's infrared, or it's gamma, or it's radio wave, or it's microwave. So I may give you a table that it gives you all the frequencies, and you have to figure out which one it is based on your answer. So if you're given, say your answer is 9 times 10 to the 4 hertz, you need to look in your table to find out which type of frequency that may be. Okay?
Wait, what is H?
H is a constant, it's Planck's constant, it's given. Remember that 6 needs to be converted into what? 6. What are the units of 6 up here, people? What are the units of the 6 at the top? No, guys, look. Look at the units here. Yeah, they're EVs, electron volts. So you need to convert that to what? What energy do we use? Joules. And there's a conversion factor that converts electron volts to joules that'll be given on your test.
This is not an 8 of pop science.